Good morning, everyone. It is 5:13 a.m. The 12th of November, 2020. As for why I'm up so early, it's not been a great week. Let's just put it that way. Not been having the best of days, but you know, organic chemistry does not wait for anybody. So let's get started. Today I'll be doing some oxidative cleavage and ozonolysis. This is probably the hardest topic so far. I don't really understand it. Well, next few are going to be pretty hard. I feel like I got the mechanism for the last few alkene things, but now it's getting pretty hard, unfortunately. So yeah. So oxidative cleavage. What are we gonna do here? So let's say we have an alkene, as we usually do in these kind of problems. Let's say we have an alkene, right? It's got this kind of structure, and we want to separate it. We want to cut this bond in half. Well, we're gonna use potassium permanganate. It's going to be warm and concentrated. Okay, and what that's going to do is it's actually going to turn into a diol like this, a syn diol. This is, well, I guess it's a glycol, diol, glycol. I don't know what the difference is. And then it's gonna cut it in half. Unfortunately, I don't really know what's going on here with the arrows, so that's gonna be a difficulty. And we end up with this structure plus what do we have here? We have a ketone and we have an aldehyde. Thing is, this aldehyde is quite unstable, and in the permanganate we're gonna oxidize it again to get a carboxylic acid. Okay, pretty simple. So I have a sort of cheat sheet on what certain molecules will, certain groups will turn into. This CH2 group will be completely oxidized to carbon dioxide and water. An aldehyde group, or I don't know what you call these things. Is it an aldehyde group? I think so. It's going to be turned into, the aldehyde, and then further oxidized. I'll just write the product actually, and it's going to be further oxidized to a carboxylic acid, like this, and then something with two R groups on it. It's going to be just turned into a ketone. Now, as for why that works, good question. I don't know. So that's a good start. That's just something I'll have to memorize, I suppose. They have some examples. Hopefully this will be elucidating. We have this thing. Okay. So if we treat it with warm and concentrated potassium permanganate, let's see, we're gonna slice it here, and that's gonna end up giving us what, like this, and then also this. And then this will be turned into Nice. Okay, and then another example. Oh, it's this disgusting molecule that I keep seeing everywhere that I'm 100% going to be tested on, that I'm not ready to. I really don't want it to happen. Oh, God. Why? Alright, so if we're going to slice here, we're going to slice here. Okay. Okay, yep. And so then that means we're going to get, from the left side here, we're going to get CO2 plus water, plus we're going to get this thing, right? That's a ketone. Alright. We're going to get an carboxylic acid, I should say, like this. 2 carboxylic acids, actually. Oh man, I can't draw. How do I draw this without? Like this. Okay, that should be what we get, right? Okay, nice. Oh, okay, well, I guess I don't have to write down the water. Okay, cool. Okay, I think I got it. Alright, and then ozonolysis. What if we want to get the aldehyde? What if we want to get the aldehyde? So, if we want to get the aldehyde from this molecule, then we actually treat it with ozone. Okay, nice, ozone. And we end up forming this ozonide molecule. Like this. And apparently I do need to know this. I need to know that an ozonide happens, I guess. I'm sure there's some stereochemical ramifications for this that I don't really want to think about. Or are there? No, I don't think there are. Hope not. And then we end up getting the ketone and the aldehyde. It's mild, so we don't have to worry about this aldehyde leaving us anytime soon. Oh. Wait. Apparently we have to treat it with dimethyl sulfide after this, so okay. DMS, cool. What am I doing? Dimethyl sulfide? It's like this. Right? Right? Oh my god, what does dimethyl sulfide look like? I'm gonna look it up. Dimethyl sulfide. Oh. I was thinking dimethyl sulfoxide. Whoops. Yeah, this is dimethyl sulfide. Okay. This was just not in my lecture anywhere for some reason. Okay, let's see these arrows here. I don't need to know the arrows, actually. I just need to know that we formed this ozonide thing. Or we can do zinc, actually, instead of DMS if we don't want. Okay, I need to add that to my notes. Okay. Alright. Okay, let's do some examples. They have a non-3-ene here. 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay. And then if we treat it with ozone, and then I guess DMS. Then, okay, if we slice here, okay, we're gonna get plus this thing, right? Okay, yeah, that's what we get. And then if we, ooh, okay, so if we do this boron, what do we call this, norborine? Treat it with ozone, then this. Then we should get a like this, I guess. Okay. Which apparently, oh, we can rewrite it as a cyclopentane with like that. Okay. Oh, and then our favorite molecule. I don't even know what this thing's called. I actually have no idea what this is called. With ozone. I would say zinc this time. Be fancy. Okay. Okay. Like this. Nice. Okay. Alright, maybe this isn't so hard. Okay. Okay, so let's see. Let's do our first problem here. Let's see. Ozonolysis reduction of an unknown alkene gives an equimolar mixture of cyclohexane, carbaldehyde, and butan 2-one. Determine the structure of the original alkene. Okay, so I don't know how to name these things, but I'll do my best trying to figure out what this is supposed to be. Cyclohexane carbaldehyde. So, cyclohexane carbaldehyde. If I do this, it's like a ketone set. I don't think that's it. Carbaldehyde. Oh, so maybe it's like this, maybe? Okay. And then butan 2-one. 2, 3, 4. Okay. Determine the structure of the original alkene. Okay, maybe the original alkene is something like this, maybe? Yeah. That's exactly it. Nice. Okay. Cool. Alright. Oh god. No, hold up. Isomerism. Could either be this one, or... Oh, right. Or it could be the other one, right? Sorry. Okay, just for fun, what's the geoisomerism of this? So if we, this is 1, 2, 1, 2. So this is the E version. This is 1, 2, 1, 2. This is the Z version, right? I hope that's right. We'll find out. Yeah, I think that's right. Okay, cool. Okay. Here are the structures of the alkenes that would give the following products upon ozonolysis reduction. I wonder why this is called ozonolysis reduction when we're oxidizing all the products. Or, I don't know. Or maybe ozonolysis reduction and the other one's oxidative cleavage. I don't know, man. Okay. So the first one, we have CH3, C, O, CH2, O, CH2, C, O, CH2, C. Oh my god, my handwriting, please. You know, this happens every time. I do this every time whenever I'm writing in real life. Ugh, man. Okay, so let's rewrite that in a more readable way. We have this. Okay, I'm not so convinced that I made it more readable, but whatever. Okay, it looks like these things were joined together or something. So it must have been like a ring. 1, 2, 3, 4, 5, 6, 7. So it must be a. It must have been a cycloheptene. That must have been it, right? Let me check. Okay, well no, there's a few more problems. I can do the other problems. Okay, and this one is cyclohexanone plus this thing. 1, 2, 3, 4. 1, 2, 3, 4. Okay. 1, 2, 3. No. Can't draw. Okay. Jeez Louise. Okay, so if we reconstruct it, it must be something like this. 1, 2, 3, 4. 2. Okay. Or okay. Wait, are these different molecules? I'm not so convinced. I don't think they're actually different molecules. Yeah, I think they're the same molecule. Okay. Okay, and then we have one, 2, 3, 4. Okay. So maybe it's something like okay, like that. Or it's like this. Or it's on the other side. These are our different molecules. Yeah, okay. Let me check the answer key. Hopefully I'm right. I was incorrect on the first one, but looks like I was right on the second and third ones. So that's encouraging. So why? Huh. God. Alright, am I missing a carbon? It says that the original thing was this. Okay. 1, 2, 3, 4, 5, 6, 7, 8. 8, 1, 2, 3, 4, 7. Yeah, there's 8 carbons in the thing that they drew, but there's only 7 in the structure. I'm probably missing a carbon. Yeah, I am. There's another CH2 here. Okay. Okay, so I guess I have to look at the carbons that are between. There are 1, 2, 3, 4, 5 carbons between, so it must be a 5-membered ring. And then 1. Yeah, so yeah, okay, that makes sense. Yeah, all right. Nice. Okay, now we're gonna compare permanganate cleavage and ozonolysis. Okay. So, time to do some predicting. E3 methyl octreene plus ozone and DMS. Okay, and then there's Z3-methyl octreene plus warm concentrated KMnO4. C. Oh, okay, well. I have to draw a molecule here. Ozone, then DMS. 1-ethyl cycloheptene plus ozone, then DMS. 1, okay, let's just say ditto plus warm concentrated KMnO4, then ditto cold dilute KMnO4. Oh, I don't know what happens if it's cold and dilute. Gotta be honest there. Maybe nothing happens. Okay. Okay, alright. Cool. Okay, so E3-methyl octreene. Okay. 1, 2, 3, 5, 6. 1, 2, 3, 4, 5, 6, 7, 8. Wait, how? This is 1, 2, 1, 2. Okay, yes, this is. No, that's not E. Gosh. I just drew the Z version. 1, 2, 3, 4, 5, 6, 7, 8. Okay, so this is E. plus ozone, then DMS. And we're going to be slicing this here, so we should get this, and I'll just say butyl. 1, 2, 3, 4. Yep. Okay. And then Z version. Right. 1, 2, 3, 4, 5, 6, 7, 8. Okay. KMNO4. We're gonna get plus right? Yeah, nice. I don't think it really matters if it's Z or not, or Z or E, right? Yeah, I don't say that's relevant. Famous last words on the exam. Okay, this plus ozone, then DMS. Okay, and we're gonna slice this here. Oh, this should be quite easy. It would be the same as if it was permanganate, I think. Yeah. Okay. 1-ethyl cycloheptene. I hate cycloheptene. Why they gotta make me draw it? Okay. Ethyl. What is this? Ozone. Then DMS. Okay. So we're gonna get this thing. Okay. And it stays the aldehyde, right? Yeah. Okay. Alright. And then what if it's with the warm concentrated KMNO4? Well, it's gonna be the same thing, except this will be carboxylic acid kind of thing. Now, but what if it's dilute? If it's dilute, I'm gonna guess that it's gonna be like this thing again, because maybe it's dilute enough that we can isolate the aldehyde? Or maybe we get both. Maybe we get both. Maybe that's what happens when we dilute it. Cold dilute, we get both. Alright, let's check. Okay. So I'm right for the first one. Right for the second one. Right for the third one. I don't know, the fourth one. Let's see. How many carbons do they have between 1, 2, 3, 4, 5? 1, 2, 3, 4, 5. Okay, yes, I have it right. And then for the second one, last one. Okay, so this is apparently what happens whenever you have cold dilute KMNO4. You get a cis dihydroxylation. So if it's like this, then we'll get. Now, is that a mechanism that I know? Syn hydroxylation uses osmium. Oh, or it uses the permanganate, that's right. Yeah, I completely forgot about that. Yeah, and it's cold dilute permanganate, huh? Let's see if I'm right. Syn yeah. Well, it uses cold dilute permanganate and also hydroxide. Okay. Alright, cool. came to my attention that I should probably have bundled in the next section with this one, but I think I earned this stream short. Study up on the next topic, and then get back right at it. So, thank you for watching. Have a nice day.